I appreciate the opportunity to be here, and I'll talk a little bit about some of these general issues that Steve raised, but you should, I think, hopefully, given the discussions you've been having in this program, it'll be your job to kind of pull some of those out of me as we go along. And I'm happy to kind of entertain some questions as we go through the issue. As Steve said, I come at this as an economist. The program I work in is an interdisciplinary program, the program I run, but more from the interdisciplinary from economics and science. So modelers of ecosystems, models of atmospheric chemistry, models of climate, and a bit of political science, but not so much some of the sociology and other sorts of aspects that I know some of you are dealing with, having talked to some of the students this morning. I think those are very important issues, and so there is a kind of probably a gap between what I do and what some of you are doing in many ways, both the scale we're looking at the problem, but I think, as Steve and I were talking, there are some interesting similarities. We're dealing with the same problems at different scales. And in some sense, the methods and methods are different when you're looking at those scales, at different scales, but I think they're tied together. I probably gave you some title when I sent it up later, and as I was putting together, I didn't remember what that was, so the title I have on my slide may be a little different than that one, but the theme is the same. So, coming at it from, the economics of land use change, I guess we think of this as kind of we're thinking if you need more land for some reason, you have more population, you're kind of introducing a big new use of land like biofuels or something. We talk about the extensive margin. That's you can convert unused land, native natural forests, to cropland or to biofuels for pasture. And there is a lot of still largely unused land on the planet. I was reviewing some FAO data, and FAO was arguing that there's still, or calculating that there's an amount of potential cropland equal to all of existing cropland. So at least in the FAO perspective, the idea that we're running out of land absolutely in some sense is not true. But of course, the issue is we're concerned about the implications of trying to use all of that land. As my colleague Jerry Melillo at Woods Hole, we work a lot with, says, are we really prepared to, use most of the net primary productivity, cycle that through human systems instead of it just being a natural system. So the extensive margin is one area, and the other side of that is the intensive margin, the ability to increase the intensity of production on existing land, get more from less. And that is largely, I think, as Steve was hinting at, the technology issue, right? So it's kind of either using existing technology in such a way that you get more production from land, or improving technology in such a way that you can get more. And one of the things I think we've observed there is that, livestock production is a very extensive user of land, and the amount of production you often get is relatively limited. So that looks like a huge resource, a potential resource for land, which could actually be, again, depending on how you look at it, ecological improvement. A lot of pasture and grazing land is relatively degraded, and moving that to some sort of managed land could actually improve the carbon storage, maybe even improve the ecosystem qualities of it, reduce runoff if you're overgrazing, and other sorts of things. So there are ways to improve our management and reduce somehow the environmental implications of it in some respects, and still have production. So it is a question of, can we integrate these things more? With an external forcing, as I mentioned earlier, increased demand for land, we expect movements on both margins, so less than a 1-for-1 conversion of land for every new hectare. So that's kind of the good side, though we want to ask what this intensity means. And then if we squeeze more things into the land, we expect prices of land to rise as scarcity becomes more and higher food prices. So that's the other margin in which we can see some things, reduced demand for food or the crops that, or the other products that use land, with whatever consequences that might have, of course. And then, of course, the carbon implications of biofuels or other expansion involve energy to improve land, to grow the crop, to convert biofuels, change in the carbon stock of land. And one of the things we've seen with the modeling we've done is that can go both ways, of course. If you cut down a natural forest with just stock of carbon, it can increase. You would lose a lot of carbon if you have degraded land and you are growing a woody crop or a grass crop. Even if you're harvesting the biomass off, you can actually increase the carbon store in the soil through that process compared to what was there before. So, Steve asked me to reflect on the uncertainties. Well, we're uncertain about all these things, right? So we don't know what the state of, we try, in our ecosystem modeling of it, our ecosystem modelers actually go back and try to kind of investigate land use. We don't really measure the stock of carbon on all the land on Earth. We don't really know. So they've gone back and simulated from starting in like 1500 the process of land conversion, land loss, land change, how carbon stocks have changed. So they have an estimate of the current state of carbon on land based on their history of land use and their simulation of the processes. But in truth, I don't think we really haven't validated that stock against real data. So that is obviously one of the uncertainties. And then the social and technological opportunities that determine whether we're going to convert land at the extensive margin or intensify production. We have some evidence on that, but we don't really know that in great detail either. So we've summarized this willingness in a paper we did, I think one I sent along, the paper in Science, 2009, I think. We did two different versions of the land model. One we called the deforestation version, and one we called the intensification process. And that represented two different ways of representing this willingness to convert land. One where we just looked at the raw economics. If it was economic, you would convert it, and became economic, you would convert it. So there wasn't really any social resistance to converting. There was some value loss because we endowed some value with that land. But if production drove you there, you would do it. And the other way, we inserted an elasticity in that process, which slowed down the process. And we based that elasticity very, very simply on we looked at the last couple of decades, said, land prices have risen by X, and over that period in this region, in each region, there's been this much conversion. So that allowed us to create a little quasi-elasticity. So those ranged from almost next to nothing in places like the United States or Europe to an elasticity of like 0.6 in the developing countries. So you've seen a lot more land conversion there. But that elasticity is capturing lots of the social processes that I know some of you study. What is the enforcement of land laws or laws against conversion? What are owners of land? How do owners of land think about that? What are they willing to do or not do if someone comes along and offers them a price for cutting down their forest or a price for the land? Are they willing to do that or not? Is there land? What is the land tenure? Who controls it? We've kind of simplified that all away by saying we'll take some observation and say here's an elasticity, and that kind of summarizes all of those processes. But of course, it's a very reduced form estimate. If those rules and laws change, if people's views change, then those elasticities can change. We did another version of the work where we actually tried to take data that kind of embodied in our model the recreation, hunting, fishing, wildlife viewing valuation of land. So there we have data in the United States on how much people spend in those activities, and there's quite a lot. So we're able to kind of then create a value for that land, for forest land, for those purposes, and then we're able to insert that into the model. So then as people's incomes grow and as population increases, there's more demand. That's an offsetting demand, an ecosystem value of that land, which can offset the demand for conventional production like crops or biofuels, and offers an offset. So that's a way of making more explicit some of the things that may lead people to not want to have land deforested to maintain in forests, although again at very large levels. Then of course and the intensive margin issue is, how much more can we get out of land? And that is, a complex issue of, if we applied more fertilizers and nutrients, could we raise crop yields with existing technology? If we have grazing land, can that be converted to cropland? What would be its productivity? What sorts of investments would we have to make in it? So those are all the huge sets of, underlying this very simple framework we've set up with a series of elasticities. Those issues are there. And then, this economics of land use change, one of the things that's motivated a lot of this work in recent years has been this big push for biofuels. Are they a good thing or are they a bad thing? And so, so the debate there is, maybe if we produce them sustainably, well, what does that mean? And so Europe has pushed, well, we won't allow food crops to be used to produce biofuels. And it shouldn't have led to deforestation. And it should be produced it should support small landholders. Well, the question is, can you really create rules that enforce that? And so this indirect land use effects, is an argument that even if you do that properly on a particular parcel of land, moving that land into that process means some other land has to be used for something else, and you're not regulating what's happening on that land. So trying to regulate this, so it's hard to regulate this indirect use of land by regulating the rules about which you, just on the biofuels. So it's kind of a really inefficient way to kind of create that regulation. From an economic standpoint, we'd like to kind of, if we're worried about deforestation or forest fragmentation or other things, we should deal with that directly. If we could enforce that directly, then we could let biofuels go, and if they became economic, they become economic, but they wouldn't be allowed to create that externality, that loss of forest land. If that caused land price to go up, and it made biofuels economic, so be it. But they'd have to dealing with essentially internalizing the externality, but creating the rules on the end product, aren't that effective. And so then, it is this multiple demands. As I said, some of the different things we've thought of, recreation demand, the carbon value of land storage, and we haven't been able to do a lot with the ecosystem value, just what those values are hard to kind of lay out. I know many of you are giving some thought of that. Just as an example, though, we've thought of the carbon, biofuels, and conventional forestry and agriculture. So how do we come at this thing and the modeling system we use? And so this is this integration of the system. I'm an economist. We have this model of the macroeconomy, the global economy, resolved for large countries and regions of the world, United States, China, Europe, Africa, Latin America, Brazil, that sort of regional level. And then we have this coupled ocean atmosphere model and represent the biophysical land processes, how changes in land cover will affect the radiation reflectivity of the land and the hydrological aspects of the feedbacks to the climate system, as well as then the agro-ecosystem processes, how the climate and weather will affect plant growth, net primary productivity, carbon storage, et cetera. So what are the connections? So this is our work. How do we see these connections happening? We think GHG, greenhouse gases, and other pollutants affect the climate. That changes the climate, changes these, and has implications for the agro ecosystem, the plant growth and productivity. So plant growth and productivity is from a commercial standpoint, crop yields, bioenergy yields, forest productivity, pasture productivity. So that has its feedback back on the economic system. If your farm is growing crops and now because of climate change, it produces less, the yield falls, you then have to do something different. Some more land has to be used, market prices go up, things change. So we feed those yield changes back into the macroeconomy, this economy model. From that, we get some sort of way in which changes in demand, in how much land is needed for these different activities, resolving the markets across trade across regions and among different uses of land, forest productivity, and then we have a kind of an algorithm for downscaling this back to the level of which our agroecosystem model happens half degree by half degree. That then reflects the changed land cover and land use, which then, of course, has its feedback back in terms of our methane, nitrous oxide, and carbon dioxide, which, if we're trying to kind of control those emissions, forces us to kind of make more reductions elsewhere for increasing those. So that's the way we kind of have looked at the land system and how we've tried to model it. So it's an interaction of the natural systems and the human systems. I guess I'd run through just then an example. Well, then following on that, how do we look at land in this economy-wide model? So this is the fundamental modeling data set or database or structure that we start from in this macroeconomic model. This is what we call a social accounting matrix, or SAM. So in this section, this is a traditional input-output structure. So this is every industry in the economy on the rows and the columns, and so a row is telling you how much is being produced of some good. If this is crop, if this is, I'm losing. If one is crop production, then that's telling us how much crop is being produced, and then the column is telling us how much of all these other inputs it's using. So it's using some fertilizer, it's using some machinery, it's using some whatever you might think along there, and then it may be using some imports. This is this column, and then it may be using labor, capital, and natural resources. So the natural resources where land comes in that sort of thing, and then that good, that crop production may be used in lots of other industries. It may be, there's a food production sector there, so a food production sector takes crops and produces food out of it. Some of it may go directly into private consumption, government consumption, or a lot of crops are used in the livestock sector, which is another sector. So this system captures this inter-industry matrix of demands, as well as then final consumption, needed for investment or government consumption or private consumption, and export. So imports, exports are there. So when we have these then changes in land for crops, pasture, productivity, that can be affected by environmental change. And you see that we then have rippling through the whole economy, right? So then as a result, it might reduce crop yields, but that's going to change the prices of crops for livestock. It's going to change the price of crops for the food industry, and ultimately change consumption. If you need, you may, if land productivity goes down, you may substitute more labor, more capital, more other inputs, but that will draw those out of other sectors of the economy. So there's no free lunch in this system. All of the inputs and resources are accounted for. So if you need to use more in one sector, you're using less in the other sector. So that's the framework.
Where do the data come from to populate the cells?
So this is the national income product accounts fundamentally, which there's a system of international accounts. Almost every country maintains those. That same system, a few countries aren't in the system very well, like North Korea. Places like that don't enter the data. But the U.S. Bureau of Economic Analysis is the keeper of those accounts. Places like USDA provide some of the data on the agriculture sector, things like that. So that tends to do very well on the market economy. Some of the things, the innovations in our program have been to try to add the non-market economy to this. So we usually think of the environmental effects as being outside the economy, but when the climate changes, if it changes natural resources that are being used, the productivity of natural resources that are being used, then it has a market effect, so we can track that effect. So this is there. Then, we may also think of unmanaged land for recreation use or degradation of quality of that. So that then has to be, as we simulate forward, we want to talk about degradation, that has to come from somewhere else.
How do you calculate the values for things like recreation?
The values?
Yeah.
So there we've gone back to these, the Forest Service in the US collects data on hunting, fishing, and wildlife viewing expenditures. So that is essentially, if you're in environmental economics, there's something called the travel cost method. And so essentially that's adding up all you spend on it. There is really not much of a fundamental value of the land itself. It's what you're willing to spend on it. And the land's value is determined by its scarcity, right? So how much is there? It's a kind of a endowed factor. You're not producing it, but if it's scarce, then it has a value. So in order to kind of make this work, we had to endow the value of we had to give unmanaged land some value. So, and this is one of those data uncertainties, right? How do we do that? Because there's really it's not really valued very explicitly in markets because we don't see it traded. It's big tracts of unused land in the middle of the Amazon or in Canada. So there is data on what the timber value of the land is. And also then, if you were to harvest timber for it forever, what's the present discounted value of that stream of timber over eternity, right? So we said, well, if the current stock of timber on it is harvestable. So we took the infinite stream value, took the current timber value off because that is not really the land, but the land value then we assume to be its value to produce timber forever there, and so that's the residual value. So those end up turning to be very, very low, like really kind of tiny. And then so that was the exercise there that gave the kind of fundamental value of the land, this potential, this I guess you'd call it option value of producing timber over indefinite future. So that was the technique we used there. Although in order to make this work in this model, we had to be able to. If we just said the land was worth nothing or it wasn't anywhere, then it didn't enter into anything. So we have to enter it into somehow into the preferences of the household and to get it in. So that was the technique we'd done there. A lot of work. This is kind of a unique way of doing it. very little work actually treats all the land holistically. You know, we have a lot of agricultural models that have cropland in them, and then they just have land that can become cropland, but they don't really tell you where it comes from. So, and we have forest models that also have supply functions for land, and it kind of comes from somewhere, but we really don't account it all. So in this system, we wanted to, since we're thinking about the whole globe, we want to count everything. So that was the kind of, I hate to use the word trick, but technique we used in order to get land into the system and have it have some initial value. That even though otherwise it's just a free good and doesn't have anything. Were there some questions back there?
I had a specific question. The medical services for health pollution, how this came under the domestic production, and how this is also linked to the land?
Yeah. So I borrowed this. This little graphic comes from a thing we've done a variety of things on. And so the medical services in this is not really necessarily related to the land problem, but in other work we've done, we've tried to, again, the broader question of trying to kind of introduce non-market effects within a market economy model. So there we've taken air pollution, and then we have people getting sick and ill from air pollution. And so then how do we introduce that into work like this? Well, those people, it affects the amount of, so if you get sick, you're not going to work, so we account some amount of labor time that when you're ill or you're not, and then you're also demanding medical services. So there is this kind of odd misconception of how economics works floating around in the world that says, air pollution and divorce is wonderful because it creates jobs for lawyers and doctors, right? But in this system, it isn't a good thing because when you demand those resources for correcting your health or solving your marital problems, that means people are those physicians or doctors or lawyers or those resources are unavailable to produce other things. So it's a loss to the economy, right? So in that sense, there is GDP activity occurring, but it's taking resources away from other parts of the economy, so it's reducing welfare. So we make a big distinction between a welfare measure, which is correctly counting those, and a GDP, which is just activity. And so if you have the other example, if you have a hurricane and it destroys all your housing, and then you have to rebuild it, that creates a lot of economic activity. But you would have been better off not having your house blown down and using all that labor and resources to build another hospital or whatever.
Back there. Maybe slightly technical, but where you put it, you call this a social counting matrix, and that's basically what you're showing up there, which is generally kind of a static thing, but it doesn't necessarily allow for price changes. It's not dynamic over time, and I'm wondering, but a lot of things you're talking about sound to me like it's sort of a SAM plus, maybe a CGE model, maybe. Yeah,
we have a CGE model. So okay. The SAM is the basis for that.
So that's the core of what
yeah,
you're doing, but you
yeah.
allow for dynamic
yeah.
change.
Yeah. So this is the base data. We have a CG model, which is recursive dynamic, so it goes forward. So there's elasticities of substitution between these inputs. There's investment here, and so investment and savings that affect the amount of investment enabled and allow growth over time. And we have labor productivity and land productivity and energy productivity as exogenous independent factors, which Steve mentioned the technology issue. Those are the kind of the trillion-dollar questions. What are those productivity rates? What are the technology, that supports that? And when you look at the land issue, if you do these models, you'll have population and growth and economic growth, and that will create a demand for food. What you assume about productivity or how you model productivity will, if you go out, particularly as we do, like 100 years, if the demand for food is growing, exponentially, but ever so much faster than productivity, then prices will go up forever. If you switch it around a little bit and productivity a little bit faster, then prices will fall. So that is the big question in these models, just what's going to happen to technology, and then also whether it's exogenous or whether the technology response is actually endogenous. So we have a bit of both. We have exogenous productivity growth for labor, land, and energy, but then we have this substitution, which you can substitute other inputs for land. So that's an endogenous response. You get a higher yield in that simple one-factor thing by substituting capital and labor for land. So you have both factors going on. But how you model that will depend a lot on how, it's a huge uncertainty about whether it's exogenous or whether it's endogenous, and that will greatly affect your results. If you think most of it's exogenous, then you can put a nice scenario going forward that's doing X, and then you put more biofuels in. Well, that means you're not going to get any of this intensification. It's really going to push most of it to the extensive margin, because you say there's really when I see this greater demand for biofuels and prices rising, that's not going to stimulate me to do anything differently. And so that's going to be a different effect than if you think most of it's endogenous. So if we look back over the history of, this is kind of getting down to these fundamental data or empirical questions. If you do econometric work to kind of tease out these elasticities, and you look at, and there's a lot of work done that looks at, the yield response, is that responsive to price? If you just do annual data and you look to see that, people who make those estimates find almost no effect, right? They find a very tiny elasticity. There's a group at Iowa State that has a FAPRI model. They had no elasticity for a while. They've now put in 0.1. You look at the longer term history, and you see that if we had we had big food price increases in the 70s, and then you saw a tremendous production response, so food price collapsed afterwards. So if you look at that longer term history, it looks like, well, maybe the thing is really responsive. But you have this kind of long, in the technology area, we talk of it may respond to price, but with a long and variable lag. And so once you get trying to statistically estimate that, and you have to, and it might be a lag of 5, 10, or 15 years, you need an awfully long data series and awfully good econometrics, statistical techniques to really understand whether you're separating out, whether you're getting a response or it's just some a response to the price or just something separate. So that is one of the big uncertainties. And then ultimately, we're talking about the land issue, but on the broader, we do a lot of our climate change and energy work, and there, if we think we're going to stabilize greenhouse gases in the atmosphere, in the very long term, that means we have to have essentially zero emissions. And so, zero net emissions. And so the question is, that's kind of a leap of technological faith, right? Either we can do it or we can't. If we can do it, at any price, then, and what the price is, if we think that's going to be cheap, then we've done this work. If some models say, well, that's going to be cheap, we're going to have learning by doing, it's going to come around. Well, then actually one of the interesting things, if we're trying to reach that target, then we don't have to do much right now. We just wait until this great technology comes along and do it then. We've tended to be a little bit more pessimistic about those, and then that says it's going to be more costly. And by the way, you better get started now because the options are going to be expensive in the future. So these technological questions really are, fundamental. And I don't know. There's been economists have tried to kind of ask, can we understand where technology is going for 5 decades at least? I think there was Arrow's learning by doing thing, or it goes back even further. I think there it really is a question of if economists could think about it, or if anyone could predict that, we wouldn't be predicting it, we'd be doing it, right? So it is kind of knowing you have to pretend to know the unknowable. So we often see models of, the kind of fad is kind of models of endogenous technical change. And we have a joke that says, yes, it's endogenous technical change, but where do you specify the technology? And so in order to have endogenous technical change, you have to specify a technological frontier and what that is or what those technologies are, and then endogenously the model might choose them or might learn about them or might develop them. But if you don't specify them in one way or another, ultimately you're specifying what you don't know. So I think models of endogenous technical change have just moved the unknowable back one layer. So that is the big question.
A couple of things. One, on that last point, it seems to me that rather than trying to get a crystal ball out, it might be interesting to know how big a productivity increase do you need not to have the thing run off the rails. That might be a more useful output than trying to pretend we know where technology's going. But on another point, it seems to me that if you look at the actual magnitudes, I'm thinking of the USA, the economic weight of the land-intensive sectors are not big enough to really let that tail wag the whole dog. I mean, and you mentioned something about putting empty land values in people's consumption funds or something. I mean, you would have to do something to trick the model to make it care, right? And I'm sort of curious how you did that. What that
Well, and you're right, it doesn't care that much in the United States. So, I mean, you can, you still want to produce those things as cheaply as you can, so there's still things happening in that market. But in fact, and the energy sector is not that big of a part of the economy either. It's a couple percent. The agricultural sector is a couple percent. So, when we look at, if you ask the question, suppose we wanted to be cleaner with energy or with agriculture, and we had to pay 2 or 3 times as much for our energy or food, it does not have a big macroeconomic effect. I mean, it's in the first place, if it's 2% of the economy and you double it, it's 4%. But then if you can make it more efficient, if you can use it more efficiently, then it's less than 4%. So 4% is kind of the maximum, extra cost in the longer run on that. Although it can have cumulative effects by reducing savings in that period and moving on. So, but when we look at these things, they're interestingly not that big of an effect on the macroeconomy. So the idea that having environmental control or doing these would wreck the economy is just a story that doesn't come out of these models because of this exact sort of idea. It's a small percentage. Other questions?
Well, one of the advantages of these kinds of models is you can break it down into different sectors and look at sectoral level impacts. And I assume that there are going to be much more significant impacts in some sectors than others with some of the policy changes or different models. And are you using it to because a lot of the politics around policy, at least, is going to be driven by which sectors are impacted, not just by the overall macro effects. I wonder what you look at those kinds of things.
Yeah, well, I mean, obviously, while I said you could double energy prices, if you put in a policy and you say this is going to double energy prices, that's not politically popular. Even if you say the macro effect is not big, people still don't want to pay twice as much for energy. So you can do that. So I mean, and it is, the CGE framework is one that has a lot of adjustment in, and we don't have that much adjustment cost in it. So the issue of, maybe you can do it. We do carry vintages of capital along and have some adjustment sorts of things, but there is an adjustment process that needs to go on, and that can be, and people, I think people have a hard time envisioning themselves in something else, right? Or envisioning, if you're a coal miner, that's your life, and it's hard to envision being something else, or maybe it's even hard to envision your children doing something else. So that kind of ability to picture the economy being very different than what it is today, I think, limits people's willingness to kind of take these on. And also, the semi-unknowable part of what it would look like is a kind of political and social challenge to those changes. So let's see. Oops. So this is a good discussion. This was getting to what Stephen wanted to talk about. I can run through this example we've done just to show you the sorts of things that comes out of this. So one of the things we wanted to look at was, one of the issues in the climate area is, okay, we'd like to reduce CO2 emissions from energy, but could reforestation be a additional help to us by growing stocks of trees? How much could that contribute to solving the climate problem? And we did this by extending carbon pricing in the energy sector to forest or all land use. So if your land use could store more carbon, then you got paid the carbon price for that carbon storage. If you were to cut down your forest, you would have to pay the carbon price. So it creates the economic incentive to use forests. So we started with a GHG pricing policy that is based on a 550 ppm CO2 stabilization target. There's a climate change science program, level 2, that was done for the federal government that it's based on. So we extended the same price level to create incentives for storing carbon in vegetation and soils. And so we looked at the implications for climate, energy system, and agriculture. We had kind of 4 scenarios here. The reference or no policy scenario where we didn't have any carbon pricing at all, an energy-only policy where we just priced CO2 emissions from energy emissions and other N2O methane and the HFCs, et cetera. And then we extended that to energy and land. And then there was one more scenario, 4, which we only did because a referee wanted it. We didn't think it was very interesting. In fact, it isn't very interesting, but a referee on the paper wanted it, so we did it. And that was to kind of say, well, let's extend this, but let's cut biofuels out of the problem completely. So this is the modeling system we have. This is kind of implementing as a model that diagram I showed you early, conceptually linking together. We have this economic model, we call it the emissions prediction policy model. It's producing anthropogenic emissions of greenhouse gases. That's going into an atmospheric chemistry climate model. Those climate factors are contributing to the downscaling algorithm we have, which was econometrically estimated. We have aggregate land use. We need NPP, we need productivity for all the cropping activities that go into the downscaling, and that leads us to this spatial allocation of land use change. The downscaling algorithm, we just did an econometric estimate that said, given the data on what land is used in each of these half-degree or half-degree grid cells, we explain that by productivity of pasture, cropland, and forests, as well as temperature, precipitation, and distance from nearest urban area. That turns out to be an important one, you can imagine, in terms of that. So and we get, fairly, for what it's worth, R squareds are R squareds. It doesn't necessarily mean a lot, but the R squareds are fairly good. So 90.9 or 0.95 in most of the regions. So that's the system, and then from that we can get net land flux, we get economic impacts, we get So this kind of starts at the end of the thing, and then we work back to see, what are some of the underlying implications of this. So this was our scenario in the absence of any policy, the temperature rising by almost 6 degrees C by 2100. The energy-only policy gets us down to about 2.5. When we add the land policy, it shaves another 0.5 degree off of it. Now, is 0.5 degree a lot? Well, if we're focused on this 2 degree target, which is what the goal is, this maybe allows us to get within that range, so it gets us something. Yes?
At 1 degree Celsius rise in temperature, you assume that there will be no net increase in emission from the sea?
The ocean is fully, we have a full coupled ocean. So the ocean carbon uptake is incorporated, or whatever is happening. The natural system, the terrestrial vegetation is responding to the CO2 in the atmosphere. And in fact, the terrestrial vegetation is responding to the climate and to ozone levels. So we are predicting ozone, and it damages crops as well. So we have that factor going on there. This is the CO2 parts per million. You see it kind of goes crazy in the one case. Here we are bringing it into those levels. And this is then what's happening to carbon in the biosphere, in the terrestrial vegetation, soils and things. In the no policy case, we are depleting the stocks of carbon. It's a source of carbon. Now there are a couple of reasons for that. Interestingly, because we have a lot of ozone and damage to crops, we have to use more land to produce food, and so we actually get quite a lot of deforestation just because we have to expand the land we're using for crops because we've damaged crop productivity. Kind of surprisingly, and then in the case where we're incentivizing carbon, this is a big. This is the forests become a net sink. So there's a huge sink there. That's the sink, and interestingly, in this energy only policy, we thought because that was kind of causing people to use biofuels and not taking account the carbon stock on land, we thought that would be the worst one of all, right? But it turns out because you're avoiding so much damage to crops, you can actually produce more biofuels and not have as negative an impact on the biosphere, on the carbon storage. So this is about neutral in terms of its impact on carbon storage. This is just the energy picture. In the no policy case, I mean, the important thing here is that this is coal, this is oil, the green is biofuels. We are getting some biofuels even in that case. The purple is natural gas. This is shale oil. So the renewables really don't come in, and we're using a lot of fossil fuels. The energy only, we get a big response from biofuels, and coal kind of goes away but comes back in with carbon capture and storage. Oil kind of goes away and replaced by biofuels. So we are getting a lot more biofuels in that policy. The energy plus land cuts down the biofuels because we're soaking up some carbon in the terrestrial system. We don't use as much biofuels. And then this is the one without biofuels, which requires more oil. We really don't see electric vehicles necessarily coming in there. So the transportation demand doesn't have much alternatives other than to use a liquid fuel, either the biofuels or the. And then this is what we have happening to. Oops, one of these didn't. Happening to this, somehow this picture isn't coming out very well. So this is the crops down here. This is pasture. This is grassland, and then this is managed forest, natural forest. And where's the biofuels? It's for some reason it's not showing up very well. I don't know why this. Let's see for this one.
Seems to be
Oh, yeah. There's a pink thing in here where the biofuels are. Unfortunately, it's showing up on the screen, but it's just not projecting very well. So one of the things when we add this, the important thing here, or an important thing, is that you see as soon as we create this incentive for reforestation, you get a huge amount of reforestation. This is the area in land and forest, and then gradually those forests grow and the carbon stock continues to accumulate. Whereas in the case of the energy only, we're taking some land out of forests, but we are getting some intensification in the story as well. Here, of course, there's no biofuels because that's the assumption. So it does dramatically, when we kind of create this ecosystem value for carbon storage, it does dramatically change the land use pattern from instead of continuing deforestation to almost an immediate.
So John, allow me to ask you, so in modeling the implications of creating policies to catalyze the use of forests to address climate change, what are some of the uncertainties associated with these results? If someone were to question you, what is buried in here in terms of what you don't know?
Well, one of the issues is just how well you could actually implement the policy, right? Can you really go out and measure well the forests and pay people correctly for that? I mean, will people get paid correctly or not? So can you measure that? How do you verify and measure it? So I mean, that I think is a big question. Can you really extend this pricing mechanism to forests?
And if we put away the implementation gap of the institutional capabilities question, what about the fluxes in carbon and the fluxes in land use?
So those come from this ecosystem model, so that's a process-based model. They try to, as we said before, there's not really, I mean, there isn't really data on the carbon, you know, there's estimates of how much carbon is in the natural system, but there isn't spatial data grid by grid of just how much carbon is there. So they parameterize their process model to, you know, sites that have good data, but there's only about 8 or 9 of them world. So the whole world ecosystems are being benchmarked to 8 sites or so, or roughly that. So that is obviously a big uncertainty. There, you know, I think probably one of the areas that we were talking about with my colleagues just the other day where we have a lot of uncertainty is, you know, we think a lot of the grazing and agricultural land is degraded. This is really, their underlying model really does not degrade pasture land, it's just natural grassland. So if that's more degraded, there may be a potential for more carbon uptake than we're actually estimating if you were to move land out of pasture and grazing into a biofuel or managed system where you're adding fertilizer or something to it, then you could actually maybe get more carbon storage. You could rebuild that land up. You know, perennial grass or something like that would give you a bigger bang than we're estimating. That, of course, would then mean maybe instead of using as much, you would switch even more from pasture into the other things because the reward would be bigger if you could actually save more out of there. So that's, I think, one of the big questions. And then you know, we're not. I mean, we're not sure of any of these estimates of carbon in these different ecosystems. They're estimates, you know, not, you know, exact. Well, we have, as I said, I forget if we were talking before or in this presentation, they go back and try to model what the system would have done over the last 150 years. But I mean, the interesting thing with that work is that if you do measurements on some of these forests, the land use history going back hundreds of years will affect the amount of carbon in the soil. So we don't really have good digital data going back hundreds of years, right? There is a set of a land database that people have created at Wisconsin that does go back to like 1750, but it's not, you know, we weren't measuring, we weren't really measuring land or we weren't recording what was happening on every acre of land going back to that time. So that is an estimate. So that's, you know, they've taken records for states or counties or cities, or I mean, you know, counties or states or provinces, and taken Landsat or satellite data for the current distribution, and then use simple algorithms that say, if it was smaller in the past, they kind of shrink it down. So is that true or not? Do we really have an accurate land history? No, but we know that the land history is there. I mean, there are questions about just how these ecosystem models work as well, right? So they kind of work on the basis that essentially, if you have stable conditions, the climate isn't changing, and whatever you're doing on the land isn't changing, that they will kind of reach an equilibrium of how much carbon is there, right? So it will kind of eventually, the amount of carbon you're adding to the system, if you're depleted, and you start growing a lot of stuff, you're adding a lot of vegetation every year, a lot of dead vegetation, and so the amount you're adding is faster than the amount that's being lost. But eventually, the more you add, the more there is to decay. So eventually, it'll come into balance. That's their assumption, but it's not.
I mean, we have a very diverse group. I don't want to belabor a point that might not be of interest to folks, but I think it could be central. So when I ask about the uncertainties embedded in this, you emphasize the ecological stocks problem and the data problem, the ecological modeling. Is there anything in the economic realm that is untested, unknown?
Well, I mean, we talked about that a little bit before. You know, the productivity assumptions. So those are assumptions whether that's endogenous or not. So how much intensification you can get. You know, we did a pre-run paper to this, was published in American Agricultural Economics, where we just varied that elasticity of substitution between land and other inputs. Makes a huge difference of whether you can produce a lot of food on a little bit of land or not. So that's
So the
a huge
sensitivity
difference.
analysis
Yeah.
to some of the economic assumptions makes a big
Yes,
difference.
yes.
And I think that's important to recognize, that it's not just the
Yeah.
ecologists are making stuff up.
No. Yeah. No. So, I mean, so those, and as I said, this whether technology is endogenous or exogenous, huge. What that response is huge. What the underlying assumption is huge. You know, are quite important. And what the demand response would be is important as well. And so, yeah. So,
Thank you.
yeah.
Now, this may be a very ignorant question because I'm not a modeler at all, but as you were talking about the forest, the definition of forest land, it sounded like maybe you were using formal statistics about what the national forest area might be in a country. And I wondered if that is the case, what about the situation of all those shifting cultivators that live in the forest and actually have a system that involves forest regrowth over a, you know, in a cyclical way? There are huge areas that have that kind of system. And are they just lumped into the degraded area with very little value? In which case the reforestation element, that hand part, may overestimate how simple it would be to, you know, it might be very difficult to do.
Well, so in the economic model, we have these we've simplified it to 5 classes of land, and the definition of forest is you know, very different. You know, in the reminds me of going back to the Kyoto Protocol when they're talking about reforestation, and you started reading the different nations submitted what they thought a forest was, and it was like, you know, how many trees per hectare and how tall they were, and so you know, and that has been an issue in some of this work in trying to kind of just say, and then our ecosystem model, that has like 33 different vegetation types. So it has things like, you know, boreal forest, tropical rainforest, mixed hardwoods, shrubland, you know, so a lot of things. So we've collapsed that in our work down to the thing. I think in terms of the idea of use, there is this, this is based largely on FAO type data on cropland versus grazing land, and so the idea that this mixed use of land is an issue of just how we address that. So we've had to simplify away from that for the main part. I mean, in principle, there's not a reason why we couldn't have more classes of land, but at this level, it becomes to kind of try to simulate the world at this level, it becomes very complicated.
I just worry about the policy implication. You know, if you say, well, if we keep all this forest and we don't let anybody deforest, implications for the people who live in the forest are pretty dire and dismal and unjust.
Well, I mean, this doesn't mean that people can't live in the forest. This means, you know, the question is whether they, you know, what they're doing with the forest or not. I mean, or, you know, so, you know, I'd say that maybe I'll get to another slide, and so we tried to kind of, so we didn't deal with that issue, but the nuanced issue of this is that, no, just what is that, I mean, what this does have implications for is that food prices rise a lot. So so we emphasize at least that trade-off. If you're going to use all this land for forests, then you do drive up food prices a lot. So we did emphasize this trade-off between the environment and food. So it's not the same issue you're raising, but we did try to recognize that this isn't necessarily all a good thing. You have to kind of worry about some of the trade-offs. Yes.
Yeah, this is the second bullet point. You pointed out that the ground level ozone as the culprit for lowered crop productivity, and there will be a mitigating measure if biofuels are used because NO2 production will not be there. As we know that NO2 plus volatile organic carbon plus light, these three produces the ground level ozone, right?
Yes.
So in a country, in a big agricultural field like as we see in United States and other areas, there will be no volatile organic carbon.
There'll be no what?
No volatile organic carbon. So unless these three things combine, there cannot be any ground level ozone.
Well, we're predicting VOCs and from our energy model, and they're being created by energy use. And so we're simulating, we simulate the full atmospheric chemistry creation of ozone.
This kind of thing only happens in big cities. For example,
that's absolutely not
Mexico
true.
City is notorious for this.
That's not true. I mean, people thought for a long time that ozone was only a big city problem, but that's because that's where they had the monitors. It's now become apparent that these ozone travels a lot outside and is causing a lot of crop damage. So once people put monitors outside of cities, and actually the ozone lasts for up to 3 months, and so there's a lot of intercontinental transport of ozone. So as you go out into these larger scales, you know, and Europe has complained that it can't meet its ozone standard because of intercontinental transport from the United States. We get intercontinental transport from China. So the ozone problem is not an urban problem explicitly. In fact, if you're in like Beijing or New Delhi and you have very high particulate and aerosols, that destroys the ozone. So the urban areas are actually have less ozone smog. They have, and it's the rural areas that are being damaged. So we've done estimates, and there are lots of estimates there are a variety of estimates of how ozone damage is currently affecting crops. And so in the U.S., estimates were, 5 to 6% loss in yields currently at the current ozone levels. In China, it's more like 7 to 13%. In Europe, 4 to 5. We did some other work on this with that. So I think that's a real effect, and it's recognized that it's causing. Now it does depend on how ozone is transported, and it does depend a lot on the transport mechanisms, which are a big uncertainty. But it does affect. The interesting thing when you get to these very high energy use scenarios, the general assumption about how ozone affects crops is that, the measure we use is AOTC 40, the accumulated ozone above 40 parts per billion. So there's controversy about this, but the long-standing idea is that at less than 40 parts per billion, there's no damage, and after you accumulate above that, there is. So the interesting results we got, this was back in quite a few years ago now, 2007, was once you get to these high levels, at the levels we have now, you aren't having that much exceedance over AOTC 40, but you have lots of places that are not that far from it. So even though we're increasing global ozone levels only like 30%, we're increasing the AOTC 40 index by 6 times, because all of a sudden you're pushing a whole bunch of stuff that was below the 40 parts per billion above it. So it had massive effects. So we've parameterized the model based on face and experimental studies on how ozone affects crops. That is a huge uncertainty, again, because different crops have different tolerances, but it does also interact with management. So fertilized crops have more damage from ozone than natural systems just because they're they're jogging out in the field.
In the interest of time, let me ask that because we have about 15 minutes left, John, do you want to present any new information, or shall we generate discussion based on what you put on the table?
Let me just finish this. So this is the the crop price, the food price indexes when you do this forest reforestation. So in the base case, even with this climate damage, food prices were increasing about 35%. we avoid the climate damage, we avoid the ozone damage, but because we're using all the land for reforestation, food prices jump 80%. So that is the trade-off between, in some sense, equity and environment. We can use this for saving the planet from climate change, but we may cause food prices to increase for the poor. So I think I can stop there and we'll open it up for data.